I've come to realise that there is a distinct lack of robots in my life. Now, I didn't go through 8 years of schooling, numerous mental and emotional breakdowns, and a panic attack for there to be no robots in my life. So, I've been thinking about robots. More specifically, making robots. And even more specifically, these things. These are servo motors. A servo motor is a regular motor with extra gubbins bolted to it that allow the user to have ultimate control of the position of the output, which is very useful for robotics where positional control is absolutely necessary. For example, this robot arm that I built. Not purely to demonstrate what I'm going to talk about now, but it's useful to do so. Oh. Easy, kid. Okay. So servo motors have three main connections. They have the positive supply, which in this particular model is in the middle, which is the red wire, which is around about 5 volts. A ground supply, which confusingly is brown, and it seems to be quite a common trait considering these are completely different servos bought from different manufacturers and they follow the same colouring. But, you know, you just kind of got to deal with some of this shit occasionally. And finally, the signal wire, which I'm going to show you on the scope because it's a bit easier to show while you're talking about it. The signal we provide to the servo is a 50 Hz pulse width modulated, or PWM, square wave. The uptime, over here, is varied between about 500 and 2400 microseconds, which gives a rough range between 0 and 180 degrees displacement on the servo. So let me just show you that here. So I'm going to twist a little potentiometer down here. You'll notice the servo, controlling the grasper, opens and closes. Pretty neat, huh? So let's actually talk about how these things work. And as my dissection volunteer, I guess it's a volunteer, doesn't have much of a choice, I'm going to use this motor, which, you know, through the act of experimentation, things are bound to get a bit rough. And this one has suffered a bit of a... It doesn't work anymore. But it's good enough to show us what we want to see. I've already undone the screws, but at least the servos that I've found normally have about 4 screws holding them together. And these screws go throughout the entirety of the body and hold both the bottom and the top of the chassis together. Okay, so if we take the bottom off, we can see these 3 wires go straight to the control board. Pull this out. Boop. And you've got a little integrated circuit there. The signal that we feed into this signal line goes straight into this integrated circuit, which on board should have some form of pulse width to voltage conversion function. There will be some form of comparator function which will take the output of that pulse width to voltage conversion, and the output of that comparator will be used to drive the motors in one way or another. Now, that motor is directly connected to the gear train, which hopefully leads our output. This is where we end up attaching our output devices to horns. That's what we call these little white plastic pieces, or, you know, whatever colour plastic pieces you end up getting, whether or not they're plastic or metal. But importantly, in that gear train, partway through, there is a connection to that potentiometer that I mentioned before. So here we have a 3-pin potentiometer, and a potentiometer is a variable resistor with a centre tapped point where the wiper goes across the resistive element, and will allow you to get a varying voltage dependent on its rotational position. So the output of the potentiometer is driven by this gearbox. So therefore, as the gearbox rotates, potentiometer rotates, and the voltage on the wiper, which I believe is this middle pin, will also change. So ultimately, the servo will take this pulse, convert it to a voltage, then it will compare that voltage to whatever voltage is on this pin on the potentiometer, and the comparator will try to change the motor's position so that it can change the potentiometer's position, so that it can change the voltage on the potentiometer to be the same as the voltage we get out of this pulse width to voltage converter. And then effectively, that's how it maintains positional control. By trying to get these two voltages to be the same, it inadvertently controls the rotational position of this output. Okay, so in general, servos are pretty good. They're pretty simple to control, and they more or less, just when they change in package size, that's about the only difference that they have. They require a bit more power, if they're larger typically, and a lot of the time the larger ones have higher torque capabilities than their smaller counterparts. However, this doesn't mean that they are without issue, and one of my main points of contention with the way servo motors have been designed is through their designed-in failure point, or rather their lack of a designed-in failure point, or as far as I can see. So I've had a number of servos fail in the time that I've used them, and I can't see at least a sensical designed-in failure point in all of them. Given they've all failed in slightly different ways, under slightly different conditions. You know, you live and you learn and all. Just before I get too far ahead of myself, a designed-in failure point is in a system. You would expect the engineers who have designed the system to have considered in what ways the system may fail. And if you think about it, a system is only as strong as its weakest component. And you can take that to your advantage when you're designing something so that the weakest component is something which is easy to replace and is quite cheap, even if it means the whole system falls over when it goes. So, for example, in this servo, there are a number of points where the servo could fail. The servo could fail on the output, though I've never seen that, where the actual plastic output, let's see if I can get a proper close look, is ridged, almost like a very soft gear. It's so, you might be able to see it a little bit in there. There it is, just a tiny bit down there. So you could have it, and if I had my way, that would be my failure point. I would decide for it to be there because it's easy to access for the user out on the outside, and it should be quite easy to replace. Just to be clear, I mean I want it to fail here, because then if the horn breaks, well, I don't really care. I'll just throw the horn away and get a new one. However, there are other points inside the servo where it fails more often, where it's a tooth inside the gear train that breaks, given sometimes, well, more often than not, that's because some dickhead is rotating it from the outside. I mean, yeah, who'd do that? Or you end up putting the motor into a locked rotor overcurrent condition, where effectively the torque on the output is so high, the motor just doesn't have the strength to rotate the gearbox beyond that obstruction. And then what ends up happening there is the current effectively goes from being an inductive load, or, well, an electromagnetic load, I'll call it that instead, because it's still using DC, to a purely resistive load. It effectively just becomes a wire. The copper windings inside the motor act a bit like a wire, and they draw just about all the current that they can get. We're talking, you know, at best you'll probably have about an ohm on that thing. So if you put, you know, 2 volts across that motor, you have up to 2 amps of current draw just through the motor body itself. And that can put a lot of strain, and in fact it does put a lot of strain, on the electronics inside. And that is probably, well, I'd say that's on par, maybe even a little bit worse than having the failure point in the gearbox. Because if the electronics fail, you not only need to completely open up the motor to take it apart, you also have to desolder and carefully resolder a board, or to be honest, at that point, it's probably better just to throw a lot of the motors away and get new. At least with the gears, you crack open the top and all you have to do is make sure you've got the right size, right number of teeth, and you put it in correctly. Whereas, you know, electronics are a bit more of a faff. Just to show my point, because I have had a motor fail in both the means where a tooth is sheared in the gearbox, which was a pain in the neck, and the electronics in a servo has failed. In fact, that's how my previous servo that I showed you, the one that I gutted, that's how that one failed. So if I were to, say for example, take this robot, and in quite a believable circumstance, although I'm going to have to manufacture it myself, this robot arm could be obstructed when it tries to move somewhere. For example, like this. Okay, so it's trying to move, you can see its normal current draw. is anywhere between hundreds of milliamps to about half an amp. If I just decide to hold this motor, and I'm not going to do it for long, you can see how quickly that jumps up to even above an amp. And believe you me, these motors are not designed to handle that kind of current draw for extended periods of time. Considering I want to build a robot here, motor motion being obstructed isn't a terribly unbelievable circumstance to find yourself in. So how do we actually get around this? There are a number of ways which, at least off the top of my head, I've come up with. So first of all, and the most simple of all, will probably be overcurrent shutdown on the motors. On the supply line, you'd put a series sense resistance. You'll have that calculated to a certain value so that when a certain current is drawn through the power supply lines, a certain voltage or a particular voltage will appear across the resistance, and you'll have a microcontroller or a hardware shutdown on your control board to turn off the power supply to the motor, where effectively it will just comply and move. And most of the time it will be okay, unless it's a particularly nasty force being applied. That is pretty good because it's simple, it's pretty cheap to include, and at the same time it will be very reliable. It will detect the current, it will shut it down. However, unless you set it to a point where it gets really dear, you might find that when the servo moves, you might go beyond that current threshold and cause temporary shutdowns in the motor, which you don't really want. And then at that point it starts getting more complicated, but I digress. Next is using mechanical compliance. So mechanical compliance in the form of a spring, say. That's probably the easiest way to describe that. So you design your output so that it's not completely solidly mechanically coupled to your hardware, so that there is a bit of give when a force is applied to the physical body. So that could be in the form of a torsion spring. I have an example of one here that I 3D printed for another project. So this is for the large, what's it called? The large Digi high torque motor. This thing is meant to be driving a gear which drives into a rotational load which could easily encounter a resistance. So what I've done is I've designed this little torsion spring into the output coupling so that if something were to jam it shut or jam it stopped, it would be able to twist, and I'm not sure if you're going to be able to see this, twist and flex and comply, at least to a certain point. It will give it some relief. Spring-loaded mechanisms are good, however you may end up incurring mechanical resonances if you're not particularly careful, as I don't like to be. Or they're just plain expensive. Buying springs is a pain in the neck, especially when you're buying them low quantity, because you can never quite find ones which are just right for what you need. So ultimately, if I can avoid that, I probably will. So maybe I'll do 3D printed springs, or at the very least a 3D printed breakaway joint, so like a design point of failure like I wanted before, so that somewhere inside these linkages, if there's too much force being applied, something will snap, completely decouple the motor from the linkage and protect the motor. Now the next thing is being a little bit clever about it. There's probably some signal inside the motor which we're not utilizing, or I'm not utilizing. What you will find is when the motor is being pushed and a force is being applied to it, it will get pushed away from the point where it wants to be, or the point where the comparator wants it to be. So the comparator will respond by trying to get the motor to rotate in the opposite direction to the force, to try and lean into the force, right? So what you can do, what I'll probably end up showing in another video, is you can tap off one of the signals inside the motor, namely the comparator signal, which drives the motor itself, or the potentiometer signal, which gives the ultimate position of the output, and you can read what the comparator, or what the motor is trying to do. So that once the motor has been pushed off by force, we can have it actually comply, and instead of leaning into the force and potentially causing a locked rotor and further damage, we can have it so that the motor actually pushes itself out of the way. It goes with the force until it detects that the force is gone. That gets more complex because we need to actually, one, know where we're looking in the circuit, and two, we need to add an additional wire or set of wires so that we can get that additional sensing capability. And another problem that goes along with that is servos do a pretty good job of protecting any electronics on the outside from the noisy DC motor back EMF spikes on the inside. So we're potentially going to be exposing those kinds of signals and bring them out of the motor. So any driving electronics that we put on it are potentially at risk as well there. So transient voltage suppression is going to become something which we need to be aware of. So unless you've got the means to actually take a look, say for example with the scope, take a look at the signals in detail, I might not recommend getting brave and tapping into the signal unless at some point I find a way of making it borderline bulletproof. Okay, so that's about all I got to talk about right now. Fuck, I ain't done this before. Bye.